And last time we were still kineticing, I think. We talked about sort of the relationship between temperature and the rate constant activation energy. We saw excuse me, we saw the Arrhenius equation, which natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. These are where sometimes again referred to as sort of the 2-point version of this equation, where if you have 2 points along, technically speaking, the graphical version of the equation that we saw, or the graph that we saw, which is this kind of graph. We again can actually just kind of plug it into the formula here. A couple of things that we talked about in terms of the calculation that's important is the units here. Again, a reminder that activation energy is usually kilojoules. R obviously is in joules. So again, you typically do need to do some type of conversion there. Otherwise, you're going to be off by that factor of 1,000. Like most things in chemistry, temperature obviously does need to be in Kelvin. And that's also what is being graphed down here, 1 over temperature in Kelvin. So again, if you have 2 points, again, as we talked about, you could solve for really anything. You can solve for a rate constant. You can solve for activation energy here. You can solve for a temperature if you have the other pieces of information along the way. The graphical version is useful as well because if you do make the graph, as we talked about, the slope is equal to minus E of A over R. And I remember this should yield you a negatively sloping line. So when you do use this to solve for the activation energy, it will be basically you'll have your M times R, and it is negative. Those two negatives will turn your activation energy into a positive number, which it should always be. So again, activation energy should always end up being a positive number in that case. By the way, also, as we talked about last time, when you do this, based on the units here of R, which are in joules, when you do solve for it, the activation energy will be in the units of joules at that point. So if you need kilojoules or something like that, you can convert it at that point. You could also use the y-intercept, right, to figure out the frequency factor. So the natural log of A is equal to our frequency factor, our y-intercept there, B. So again, the frequency factor, as we talked about, is really the proportion of molecules that, again, have enough energy get up and over that activation energy hill to get to the other side. The activation energy hill, a reminder, is that hill that those reactants has to climb to get to the other side. And that's that sort of energy barrier that we talk about, that they have to sort of maintain a specific amount of energy when they do collide with each other to get up and over to the other side. Let's see here. Now, we start talking about mechanisms in the end here, and mechanisms are an idea of how perhaps a reaction is actually taking place. So, not all reactions, again, are just a kind of straight shot over there from reactants to products. It may actually be a result of several individual steps along the way or several individual reactions. And those reactions are what are referred to as elementary steps. So, for example, this reaction may occur by first making C and D and step one. And then maybe in step two, C and D kind of go away and we make E and F. And again, we can get the overall reaction by adding these together. Anything on opposite sides of the arrow that are the same will cancel or reduce down. And that'll leave us our overall reaction here of A plus B goes to E plus F. Now, usually in a reaction mechanism is sort of a plausible explanation of how this reaction may actually be occurring. And there's usually a slow step in the mechanism. And that slow step in the mechanism is known as an RDS, which is a rate determining step. I go that way. And the rate determining step is the slow step in the mechanism. It is really the one that will determine overall how fast that reaction is going to take place. So again, I use sort of the example of like if you were in the store and there's somebody ahead of you that had like 400 items and the 10 items or less, and you had just 10 items, your part of the reaction, right? The time it takes you to get out of that store is very quick because you only have 10 items, right? But what's really determining how fast you can get out of the store is the one person ahead of you, right? You have to wait for that him to run out his 400 items, right, and pay before then you can get to the register, obviously, and get out. So your rate of your overall reaction is much slowed down by him and the person buying those groceries. And that's what the idea here is. There's usually a step in a reaction mechanism that's really the one that's going to kind of take up most of the time of the reaction. And because it kind of does that, it's going to really determine the overall rate of that reaction because, you really can't get moving forward in a lot of cases until you get past that step. So that rate determining step is really important. And there's really two things that has to sort of happen for a reaction mechanism to be sort of a good mechanism or a plausible mechanism. The first thing is what we did here. You basically, if you take all those elementary steps and you add them together, you do need to end up with the overall reaction you're looking for. So clearly, if you add up all these elementary steps together, you cancel out what needs to be canceled out. What you're left with, if it's not the same reaction you're looking for, it is a bad mechanism right off the bat because obviously it doesn't give you the reaction you're looking for. But if it does add up to the right reaction, the second thing you have to look at is the rate determining step should have the same rate law as the one found experimentally. And usually in these are a lot of times in these sort of mechanisms, you will be given sort of the experimental rate law or the observed rate law. And that's one way you could identify in a mechanism what is the slow step or the rate determining step is it should have the exact same rate law. Now, how do we get the rate law for these elementary steps? It is the one place in kinetics where you can use the coefficients as the orders. And for each elementary step that you have, you can write an actual rate law for it. So, for example, here on step one, our rate law would be K, A, and B. And for the second one, it would be the rates equal to K, C, and D in this case. And one of those would match, for example, the experimental rate law, and we would know that would be the slow step. And that's one way that you can sort of determine it. The last thing we sort of talked about with this is remember that we do have intermediates. And again, intermediates are things that should be completely used up by the time the reaction's done. It should not appear in the overall reaction. So I think the last one we finished on, although we did cancel out like NO2, I think it didn't completely cancel out and it was still there in the overall reaction when you looked at it or equation. And that is why NO2 was not classified as an intermediate, while the NO3 did completely cancel out, was not seen in the overall reaction. And that tells you that it is an intermediate. Yes. All right, we're taking notes with that computer, I hope. Yes. If not, you better shut it off. Yeah. All right. So let's take a look at another example over here. And let's take a look at this type of mechanism. And this is sort of a secondary sort of mechanism type problem, a little bit different than what we were doing in the first example that we had. This type of mechanism problem, I would say, is similar to like a proof in math where you kind of know the answer, but you have to prove that it's a good or bad sort of mechanism. So in this reaction or this mechanism, we're looking at this overall reaction here. I'm just going to write it up on top here. And it was experimentally found that the rate law was K, H2, and NO squared in this particular case. All right, so in order to determine whether or not that this is a good mechanism or not, the first thing we have to do really is add up all these steps here, see what cancels out and what we're left with. So if we did this here, we would have our, let's see here, we would have our N2O2 and N2O2 would cancel. We would also have some N2O cancel on both of them. And I think that is all the canceling. So everything on the left-hand side here, and again, these numbers here are the step numbers, so not to be confused with coefficients or anything like that. So on the left-hand side here, just gotta put a line right there. We will end up with 2H2 plus 2NO. And on the right-hand side, we have 2 waters there, and we do have an N2. So on comparison to the overall equation we're looking for, we do see that, yes, indeed, when we add up all these steps here, we do end up with the overall reaction that we're looking at. So that's a good first step in terms of whether or not this mechanism is a good mechanism or not. The second thing that we need to know is, does the experimental rate law match the rate law for the rate determining step? Now, in this type of mechanism, in order to determine the rate determining step, it's really hard to figure out which one should be the rate determining step. I'm going to go with the one marked slow. Yeah, so that seems like a very good one to go with there. So this is the other way very easily that you can determine which one's the rate determining step. As you can see here, they typically mark some steps as fast and they'll mark some steps as slow. And usually, obviously, the slow step is going to be your rate determining step. So that means if I were to just look at step number 2 here and write a rate law, I'm going to get rid of all my cross outs here. And if I wrote the rate law there for step number 2, which is our rate determining step, the rate would equal K times H2 and N2O2. Now, we want to know, does the slow step here rate law match the one that was found experimentally? The answer actually is you don't know yet. So that's the actual true answer. And the reason you do not know yet is when we added together all these equations, right? We canceled out some things, which I guess I shouldn't erase too soon. Let's cancel out that, and we cancel out that. In this particular reaction, what are our intermediates? Our intermediates is N2O2 and we have N2O, right? Those are our 2 intermediates in this reaction. Now, the reason we cannot directly at this point compare these 2 rate laws is because when I look at the rate law for my slow step, what I find in there is the intermediate. Yeah. So I have this intermediate in the rate law that doesn't allow me to directly compare the rate law for that step to the one that's found experimentally. The old saying is you want to compare apples to apples, right? So here we're not really comparing the same things, and that way we can't really make a true judgment on it. So what do we need to do? Well, what we need to do is turn this rate law into one that does not have the intermediate in it anymore. So we got to kind of get rid of the intermediate here. And the particular intermediate we're looking at in this case is the N2O2, which the only other step in the mechanism where we actually do see N2O2 is actually right here at the first step, right? The first step is the other step in the mechanism that actually has that one listed. So we're going to have to use the first step here to sort of get rid of that intermediate in that rate law. Now, there is something different about the first step, which is if I rewrite the first step here of the mechanism, I have 2NO, and this is actually arrows heading in both directions, which means that this is a reversible reaction. It has a forward direction, which goes from reactants to products. And at some point, as we'll talk a lot about in the next chapter, those products will recombine and come back the other way. So it's like a two-way street type reaction. You got things heading in both directions. You have reactants going to products, products coming back to reactants. Now, because this is a reversible reaction and it has those arrows, we could actually write 2 rate laws for it. One in the forward direction, like the reactants going to products, and we could write a rate law in the reverse direction, which is the products coming back the other way. So if we were going to write our rate law for step number 1 here, for the forward direction, go forward here, it would be the rate is equal to K times NO squared. And again, that would be our forward direction. And if we did it for our reverse direction, in the reverse direction, since it is heading this way, our products actually become our reactants, right? And our reactants become our products since it's heading in the opposite direction. And the rate of the reverse reaction will equal K times N2O2 in this case. Any questions on that there? Now this, yeah. How do I say again? Yeah, no, it's good. Yeah, so this is still elementary steps. So again, this is the only place in kinetics where we can use the coefficient as the exponent. So that is where the coefficient came from with the square. Yeah. Other questions? Yeah. Correct. Yeah, you have to climb the hill in the backwards direction, right? So it's just like if you walked a hill, right? You got up, right? You got to the other side. They're like, oh, now I gotta go back to my car. I gotta go back up the hill, right, the other way. So unfortunately, the hill doesn't move, right? So it's just how much you gotta go up it, depending on which direction you're going. But it would be going in the reverse direction. You would go back up the hill because in that reverse direction, this technically would be kind of like your reactants. This would be your products, right? So these guys gotta go back up that hill the other way, basically. Yeah. All right. Now, because this is a reversible reaction, if we want to use our actual, we have a little difference in the K's here. Going in the forward direction, they call this K1, and this is K to the -1. Now, what will eventually happen in this reaction, and again, we'll talk a lot more about it in the next chapter, is eventually this reaction, because it's reversible, will reach what is known as chemical equilibrium. And basically what chemical equilibrium means is the rate of the forward direction in this reaction will equal the rate of the reverse direction. So eventually this will reach equilibrium, and basically you'll have the rate of that forward direction will equal the rate of the reverse direction in this case. And that's going to be really helpful for us because although we do not know what the actual value is for both of those guys, should they be the same number or the different number? If eventually the rate of the forward direction equals the rate of the reverse direction, should be the same number. So because those guys are going to be the same number, what that allows us to do is set the other part of the equal sign equal to each other. So we could actually set this guy equal to the other part of that one. And again, that is because the rate is really the same number. Now, remember, the goal of what we're trying to do here, right, is the goal is to get rid of this intermediate. So at this point, what we have to do is solve for the intermediate, which is this. That means we just need to divide this to the other side, right? So we're just going to divide that K value to the other side. That will give us that the concentration of N2O2 will equal K1 NO squared divided by K to the -1. Any questions on that there? Yeah. It is a subscript, yeah. The K1 you're talking about, the K minus, they're subscripts, yeah. So they're these guys right here. Yeah. Other questions? All right. We actually now have something that we could substitute in. So what we're going to do now is we're going to take what we just solved for, which is basically the intermediate, this whole thing equals the concentration of the intermediate. We're going to take this whole thing and drop it right into our original step 2 rate law that we did. So if we do that, I will write out everything individually here. The rate will equal K times H2. And now we're going to substitute in what we got over here. That's going to give us a K to the 1 NO squared and a K to the -1. All right. So we can actually do some reducing now because we have a bunch of little k's, right? And the little k stands for the rate constant. So again, should that be the same number or a different number? Same number, yeah. So although again, we don't really know what the number is, we do know I got a rate constant on top and a rate constant on the bottom. It's going to cancel out. And now we can really simplify this to the rate is equal to K. Whoops, if I write the right thing, H2 and NO squared. Now we have a rate law that does not have the intermediate in it. And now we could actually compare it to the one that was found experimentally. So this is the one we just did through substitution. This was the one that was found experimentally. Do they actually match now? They do. Yeah. And that's why I said earlier, you don't really know if they match or not because you have that intermediate in there. So you cannot do that comparison with a rate law that typically has an intermediate in it. Gonna has to do the substitution type thing using other steps of the mechanism to substitute out that intermediate, then you can kind of compare it. So because we went through this whole process here, we have now met the two things really required for this to be sort of a good mechanism: the overall reaction balance and the rate law for the slow step and the one found experimentally actually matches. So this is I'll call it a good mechanism. Yes. Are what they usually will call a plausible mechanism, right? So they'll say this is a plausible mechanism as to how this could occur. Any questions on that there? Fun times had by all. All right. All right. So, I tried one. Why don't you try one? See how you do. Yeah, you do. Yeah. Yep. You can. I just keep it all the way so you can see where everything ended up. Technically, you can, and it does cancel out, and you do end up with that. But I just kind of waited to the end. Yeah. Other question? Yeah. Yes, that's why they're called the rate constant because they're a constant value, right? So, and it will be a constant value as long as the conditions of that reaction don't really change at that particular temperature. Yeah. Say again? Yeah, so they are ultimately the rate constant, even though these are all made up of sort of individual steps. That particular one is based on the rate constant for the overall reaction, and they will be the same. Yeah. The rate constant is uh it is sort of independent of what's going on. It has to do with sort of the reactants that are present, and obviously the concentration of those reactants can determine make a big determination on the overall rate of it. But it's sort of a constant value for that reaction, which you know is kind of set in stone as long as the conditions don't change. So you always sort of end up with sort of a similar rate constant all the way through. It should. Yeah. This rate constant is really for really. So the idea here is these are the steps in the mechanism for this overall reaction that we're talking here. And these rate constants are really based on kind of that overall reaction that's happening. And they're just made up of these kind of individual steps. Yeah. Yep. Good question. All right, now you try one here and see what you come up with. All right, we have I'm not sure why the T didn't go down, but we'll put the T there. So we have this reaction 203, a little ozone makes 302. Experimentally found rate law is the rate is equal to KO3 squared and O2 to the minus 1. It is believed to obviously occur through these two steps here. I guess determine if this is sort of a plausible mechanism, a good or bad mechanism here. So take a few moments there, see what you end up with. To be a sort of good mechanism, a plausible mechanism, two things has to happen. You have to, again, have the elementary steps here add up to the overall reaction. So we might as well just start with that because if that doesn't work, there's no need to go any further, basically, at that point. In this case here, we will see O, looks like, as the intermediate. And that's going to give us now, everybody on the left there, 203 goes to 302. So yes, it does match the overall reaction, so that's good. Once again, we can identify the rate determining step because that again is the slow step in the mechanism. And again, that is the rate law that should match the one that's experimental here. And if we wrote it for that, which again, from the elementary steps, we can use the coefficients as the exponents. And we'll have K times O3 and O in this case. Any questions so far? At this point, we want to compare, but once again, we cannot directly compare because, again, what we have here in our rate law for our slow step is our intermediate, right? So as we saw here, that guy completely canceled out, and that's our intermediate in this case. So much like the last one, we need to basically substitute out that intermediate for something else and then make our comparison. In this case, you have pretty much one choice, so that makes it pretty simple. You do need to go to the first step here. This first step here, again, is an equilibrium reversible reaction step. And we can, again, write the rate law for the forward direction, which would be going in this direction. And that would be the rate. Oops, rate. Try that without the rate twice. That would be the rate is equal to K, and I'll just use a little subscript there, K1 times O3. We could also write it in the reverse direction, heading in that direction. And the reverse direction would be the rate in the reverse direction would equal K to the minus 1, O2, and O. Questions on that so far? Yeah. It is, yes. Yeah. So I'll show you that in just a second. A little bit more. So when we look at this, because again, this is a reversible reaction, this one, it will, and sometimes you'll even see them actually write fast and it'll go write equilibrium next to it. And that again means that the rates there of the forward and reverse direction are going to equal each other. And once again, that is what's going to allow us basically, because these are both the same number, that's going to allow us to set the other side of each of those equal to each other because they do equal the same number. And in this particular case, we want to really isolate the O because that's the intermediate. So we're going to take everything here and divide it to the other side. And when we do that, we'll end up with K1, O3, K to the minus 1, and O2. And that is going to equal the concentration of O. We once again here now have something that we can put into here and substitute in. And if we do that here, we will end up with the rate. And I'm just going to write everything in here, KO3. We got K1, we got O2, not O2, O3 there up on top. And K to the minus 1 and O2 on the bottom there. Doing some cleanup here will give us, those guys will go away. These are both O3, which means we will end up with K O3 squared divided by O2 as our rate law. And now we can compare it to the one that was found experimentally, and do they match? They do match. Remember, something to the minus 1 is 1 over it, right? That's why it's on the bottom there, right? And right there. And so they do match. And that means, again, it is a good mechanism in this particular case. Any questions on that there? Yeah. You only have one slow step. Yeah. So there'll only be really one step that will determine the overall reaction, and it's the rate determining step. So you usually only have just one slow step to choose from. You may have multiple fast steps. You may actually have, for example, like the first one I did, I think we had maybe like 3 or 4 steps or something like that. So it's possible you could have mechanisms that have like, 5, 6, a ton of like steps along the way. You may not have to use them all. I would say in most cases in a mechanism problem like this, you would use that reversible reaction as to the one that you would use to try to substitute out. Any questions on that there? Yeah. This type of one, which I'll call kind of like a proof type of mechanism here, usually will have something like that, or a way that you could substitute out for something else. The only way you really could substitute out is you need that reversible step. So they should definitely usually have it. Yeah. There are kind of three different types of mechanism problems. Like this one is a lot different than obviously the one that we did at the end last time, this one, right? So there was none of like, kind of that thing. You could just from this one, because directly step number, I think it was step number one matched the rate law just straight out of the box. You didn't have to do any of that stuff. And this is sort of a different type of mechanism problem than obviously like the one that we're doing right now. Yeah. So when we look at a reaction such as this top one, which is, like I said before, the topic of the next chapter. This is again a reversible reaction, and when the question is K1 and K minus 1 basically equal to each other? And we can write again our rate law for each of those, like we did our forward direction, where K1 and O3, and we could write it for our reverse direction. The rate of the reverse direction is equal to K to the minus 1, O2, and O in this case. And just like we did before, we could set them together, right? And for example, do this. There's a couple ways you could look at this. So one way, for example, is if I solve for um, K to the minus 1 just by itself, right? I would take this guy and divide it over there. So if I solve for K to the minus 1, it would equal K1 O3 and O2 and O. And if I substituted this in for K1, right, I would put this in and I would end up the rate of the reverse reaction would equal, in this case, K1 O3 and my O2 and my O. And I would still have this there times up on top my O2 and my O, right? Those cancel, those cancel. I now see that the rate of the reverse reaction equals K1 times O2. And we know that the rate of the reverse reaction equals the rate of the forward direction, right? And the rate of the forward directions equals that. And I think I wrote the wrong thing there. That was O3 up on top. My bad writing there. So I actually put the O3 there. And now we can see that the rate of this guy here basically equals that. So they're basically both the same in this case. If I wrote much neater there, my 3 there, right on my 2. So that's one way you can look at it. The other relationship is, as we will see in the next chapter, the main topic of this class and how it relates to the rate law is if you took those guys equal to each other and instead of solving for one of them and then popping them back in there, if you actually solve for this guy divided this way and this one that way, that gives you basically the K1 over K to the minus 1 equals our O2, our O, and our O3. This relationship is a really important relationship. This is essentially the K of the forward direction and the K of the reverse direction. This is what is known as capital K. This is the equilibrium constant, which is again the main topic of the season, is what this is. So if you take the rate constant in the forward direction divided by the rate constant in the reverse direction for a reversible reaction, it will actually give you what is known as the equilibrium constant, which is a constant value for that reaction at a specific temperature. It will always be the same number as well. So these are how the rate constant sort of ties to the equilibrium, which again is the main topic we're going to talk about starting in the next chapter and on. But that's how it ties into sort of this sort of situation with the rate constant. Any questions on that? Yeah, say again. The equilibrium constant is a relationship in a reversible reaction where you take basically the products over the reactants, and it's always a constant value for a reaction, regardless of, as we'll talk about, regardless of how much you start with, You started with all reactants, all products, a little bit of everybody. If you keep the temperature the same in an equilibrium reaction, which is what the first step is, if you keep the temperature the same, you will always hit the same equilibrium constant value, no matter what you start with in terms of how much products you start with, how much reactants you start with, what you start with. That reaction will always come to the exact same number as long as the temperature stays the same. Okay. And then that's obviously the topic of the next chapter. I'm going to talk more about it there. Yeah. All right, let's take a look at one last different type of mechanism problem here. We wanted to determine the overall reaction here. We also wanted to determine the rate determining step and what the rate law should be and identify all the intermediates of the mechanism here. So I want you to take a few moments there and work that stuff out. And again, this is sort of a third type of mechanism type problem. Let's take a look. So we'll start with the overall reaction, which is just simply adding these two steps together. And in this case, it looks like B should cancel, and I think that is it. So that's going to give us a 2A on the left there, plus a B to the 2 there. On the right-hand side, we got a couple of ABs, so that's going to give us this as our overall reaction that's happening here. Obviously here, the rate determining step is the one that is marked slow. Yeah, so step number 1 here should be our rate determining step. And because that is the rate determining step, we do know that its rate law for that step should be the one that is found experimentally and should be really the rate law for the reaction, right? So because of that, we could just take step 1 and write the rate law, which is the rate is equal to K times A and B to the 2. And that should be the rate law for this reaction because, again, that is the slow step, the one that's kind of holding up the line. And obviously here, our intermediate would be B, in this case. Yeah. Any questions on any of that? So again, this is a slightly different type of mechanism problem here. So I would say, there's 3 or so types of mechanism problems. We kind of did one of each, and it just kind of depends on what you need to do on the problem. Yeah. It should not because the rate law for step number 1 is based on the equation in step number 1, and in step number 1 there's only 1A. It is not based off the overall reaction. So remember, with the overall reaction, we can't use the coefficient as the exponent. We can only use it in this specific area here and these elementary steps in each in the mechanism that you could use those coefficients. Other questions? Yeah. You do not in this situation when you're doing mechanisms. It is based on the slow step in the mechanism and the equation for the slow step. And that's what really it's based off of, because again, that's the one that's going to kind of hold up the line along the way. Yeah. It is, and it should match the one that's found experimentally for basically the overall reaction, right? Because if you're doing this experiment, you would probably be observing like the overall reaction, right? And if you did an experiment like we did in class and stuff like in lab, you would end up with a rate law that was found sort of experimentally, right? By doing the procedures like we did in class in lab. And that rate law should come back and match in this mechanism type of situation here, that slow step. I missed the first part of it. Would it be like before we got into mechanism? Yeah, so I would say that a mechanism problem is pretty straightforward in the sense that it will usually say it in the problem. I would say most cases it will actually say it like, hey, because part of the question that you usually ask in a lot of cases is, in a lot of cases, is this a good or bad mechanism? Or it will say something like, this reaction is thought to have occurred via this mechanism. And the other way you could kind of recognize it is you'll have some type of mechanism usually kind of written into the problem. You'll have something with multiple steps kind of written. That's the way you can kind of recognize it. Other questions? Yeah, it's not. So remember, remember that for overall reactions and reactions in general, the rate law is found experimentally, like you're doing in class and lab and stuff like that. Now, the only place where we can use the coefficient as the exponent is in these elementary steps and when you're kind of trying to analyze a mechanism. So in that situation, you could use it, but we do not write the mechanism, or we do not write the rate law based on the overall reaction. They don't equal each other because they're technically found experimentally. And that's why we don't use that coefficient, for example, the 2 there in front of the A in the overall reaction, because really the rate law for this overall reaction is not really based on that equation that you see. It's actually based on what's happening here in this step. So it's really based on what's happening in that step. And that's why, because it's based on what's happening in that step, you can use the coefficients as the exponents. And that's why we have something that's different than what we see in the overall reaction. And that's also why at the beginning of this chapter, when we talked about sort of calculating rate laws, we said we don't use the coefficients for it, right? And the reasons for that, because although the overall reaction may have a different coefficient for a reactant, what's really determining it may be a step in the mechanism where that's not the coefficient for that reactant. It's something different, like we see here, right? For the actual step that's determining the overall rate of this reaction, the coefficient for it's actually 1, right? In step number 1 there for the A. And it's not really what we see stoichiometry wise at the end of the reaction and the overall reaction. It's not really having that big effect on the overall rate of it. Is not the 2 that we see there. So that's why we have to kind of look at the slow step when we're doing something like this, and it should match the slow step, and that's why we're looking at it. And that's why in the end, the overall rate law may not match the coefficients that you see in the overall reaction, because again, that overall reaction is based on several steps along the way to get there. Other questions? Okay. So one last thing here before we wrap sort of this up is we talked a little about energy diagrams, and if you had like a mechanism, and we'll just make up a one here like C plus D, and this is like step 1. And we have step 2, C plus D goes to E plus F, right? So again, our overall reaction here as our intermediates cancel out is our A plus B goes to E plus F. How does that look when we sort of draw the energy diagram for what's happening in this overall reaction? We'll just say, for example, that the first step here was our slow step, and this is our fast step. And that would mean, again, here that the rate determining step is really the first step in the mechanism. So when we would go to sort of plot this, sort of energy, right, versus the reaction happening, what we would have is something like this, where A plus B here, right, are our reactants. We would have an activation energy that would come up. And then this guy would then dip down perhaps to our intermediates, our C plus D, right, are formed. And then we would have another step in the mechanism, right? I'll do something like this as I run out of room. Just come here. We'll just kind of curve it that way. It's going to take my whole line out, I know, when I hit it with the eraser. It's probably a bad choice. Just took that part out. That's not too bad. So I'll rewrite that. So this guy's going to come back up and come over to our products of E plus F, right? So a couple of things, if we look at this energy diagram, we actually have 2 activation energy, right? We got this activation energy, and we have this activation energy. Hope I drew it somewhat better. And this would be for step 1, right? And this would be for step 2. And a couple of things that we would want to note on this is our step 1 hill should be a larger hill of activation energy, right? Because again, that's going to slow down the reaction, right? If you have a bigger hill to get over to the other side, it should be a bigger hill in comparison to this one. So this one here, I did my best there, should be a smaller hill than our first hill. This should be a larger activation energy. Now, also, we could determine if this reaction is exothermic or endothermic. Which one would this one be? If we do the difference between ultimately our reactants and our products, that would be our delta H, right? And again, we have a smaller number minus a larger number there. That's going to give us a negative number. And this would be an exothermic reaction that's happening here. So you can write an energy diagram for a mechanism. And what it should reflect is uh, whichever one is the slow step should have a greater activation energy hill than the other steps. Again, the idea there is that is what's going to basically determine the rate. That's what's going to slow everybody up, right? It's a giant hill you got to walk, right? So if you had two hills to walk, you're only going to get to the finish line probably as long as it takes you to get up the biggest hill, right, to the other side. And again, that is what should be reflected if you had to draw some type of energy diagram for it. And again, it could be opposite. Obviously, if our slow step was the second one, then we would have perhaps a smaller hill followed by a bigger hill, right? Something like that. And now you can see here that step number two has a much bigger activation energy than say step one. And maybe I leave it up here, it ends. And again, our products might have actually ended up higher in energy than our reactants in that case, and it might actually be an endothermic one in this particular case. So these are the things that you sometimes will have to draw. You'll be asked to do that in the next experiment to draw some of these sort of energy diagrams based on mechanisms. And that's what you kind of want to think about when you have to draw those is, the slow step, its activation energy should be definitely a bigger hill than the faster steps. You also want to think about where your reactants and products would end up if you had to draw it based on whether or not the reaction is exothermic or endothermic, right? So that would also be a determination of where things would end up. Any questions on that there? Questions on kinetics? That should wrap this chapter, I think. Oh, no, almost there. We got a catalyst. We'll talk a little bit about it. I think we kind of talked about it along the way, but just to sort of finish up, a catalyst is, again, a reminder, a substance that really is there to speed up the chemical reaction. Again, it's not considered a reactant. And again, it's not considered a product. And it does not get used up in the reaction. It is there, like I said before, to simply find a more efficient way for that reaction to take place. And the end result of it being able to sort of find a more efficient way for that reaction to take place is it's able to lower that activation energy. So it's able to lower that hill of energy that the reactant has to climb to get to the other side. And again, by it decreasing the hill, obviously that's going to create a situation where there's going to be a lot more reactant molecules that have enough energy to get up and over to the other side, and also by default there increase the rate of the reaction again because they don't have as much of an energy barrier to get to the other side. Again, same example, if you had to choose the big hill versus small hill, most people would probably choose perhaps the smallest hill, right? And that would get more people rolling through the hill a lot quicker to the other side. Now, a catalyst can actually slow down a reaction, but most people, I would say, when they're speaking about a catalyst, are speaking about it in terms of speeding up a reaction. That's sometimes referred to as a positive catalyst, one that speeds up the chemical reaction. There are catalysts that can slow down a reaction, and those are sometimes referred to as negative catalysts, and they kind of slow down the reaction. But I would say almost 100% of the time, if you're having a casual conversation about catalysts, why you're doing that, I don't know. But if you're just having that casual conversation about a catalyst, you're probably talking about it speeding up a reaction, is usually what most people are doing with that. And again, because that activation energy decreases, we actually see an increase in the rate constant and thus an increase in the rate of the reaction. Because as we talked about, basically when you write a rate law, it's the rate is equal to K times something, right? So if that K gets larger, when you times it by whatever is on the other side, the overall rate's going to get larger when you look at the rate law, where obviously the rate's equal to K times something. So if this number gets bigger, that's going to increase the rate of the reaction by the same sort of fold. Now, there are different types of catalysts, and we're not going to go too great detail, but there are catalysts that are heterogeneous catalysts, and much like a heterogeneous mixture, That means, did you see different phases and stuff like that? That's the same idea here. The reactants and the catalysts are in different phases. So maybe the catalyst is a solid and maybe everybody else is a gas. So they're, gas molecules flying around a solid thing. The Haber synthesis of ammonia, production of nitric acid, and catalytic converters right in your car. Homogeneous catalyst. The reactants and catalysts are in the same sort of state. So sometimes, a lot of times, we'll use an acid as a catalyst, really like we're doing in the experiment in lab, but where the HCl is really being used is really a catalyst, but we kind of treat it like a reactant. But it's in the same phase as everybody else, right? The HCl was aqueous, just like all the other solutions, right, that you mix together. Everybody's in the same phase. Obviously, in a chemical equation, up on top of the arrows, typically where you'll see a catalyst written, that is being used. And here's like the Haber process here of ammonia. And ammonia, again, here is using some type of solid catalyst. And as I mentioned before, one of the roles that the solid catalyst can do is just provide a platform where all these gas molecules are sort of attracted to. And instead of them having to just kind of fly around and find each other, they're now all going to kind of come to a central location. And it also aids in some breaking of some bonds and making of some bonds. And now they can kind of reunite and come off a lot easier and more efficiently. As I said, without the catalyst being present, you got to hope that the right guys come together in the right orientation, hit each other with the right amount of energy. Again, this just brings everybody a lot closer together and facilitates that reaction. Again, just more like efficient, if you want to think about it that way, than it would if it wasn't there. Now, this process of making ammonia is what's known as a spontaneous reaction, but without the catalyst, it's a super slow reaction, like all day project is. It's a very, very slow. It will eventually do it, but you could definitely aid it along by adding a catalyst to the experiment and helping out everybody kind of get there in the right spot. This is the production of nitric acid, and they use something like a platinum wire as a catalyst. And again, that again just makes it a lot more efficient for it to go. And as you can see here, actually, it's a several step process to make nitric acid. But one of the good things is it actually makes some of the stuff that's needed in earlier steps. So it kind of self-feeds the reaction going and going on as it makes more nitric acid. Catalytic converters in your car, right? Which is why they cut right about there and maybe right about there. Don't teach that. Don't do that. That's wrong. The reason for that is there's valuable metals inside your catalytic converter, right? And good. But really, there's actually two types of catalysts, right, that your car goes through if you have a catalytic converter. Um, and it helps kind of obviously purify both some unburned hydrocarbons along the way, but it's a honeycomb in there of some precious metals and obviously perhaps valuable to some people. But do not cut anybody's catalytic converter out or anything like that. Don't do those things. So for the little time that we got left here, we're going to get into really the main topic of the class. Now that we have that little appetizer warm up there of kinetics. But really, this class is brought to you by the letter K, which is the equilibrium constant. And we're going to talk about every equilibrium constant you never want to know about. And then eventually we'll get past exam 2 and maybe not talk so much about it as much, but it'll still pop up every so often. But this is really the main sort of topic of the class. So what does the equilibrium constant really involve? It does actually involve the type of reaction that we just saw there when we were talking about mechanisms. And it involves a specific type of reaction where it is a reversible reaction. And again, it will be these reactions where you'll see these arrows heading in both directions. As we talked about there at the end of the last chapter, there is what is considered a forward direction as you go from reactants to products. And as I mentioned, as this reaction really starts to take place, you're going to start to make some more products. And eventually those products will actually recombine and actually head back the other direction. And you'll have, as we go in the other direction there, what is referred to as the reverse direction. And eventually this reaction is so self-sufficient that it will always reach equilibrium. Yeah. So no matter what you do to it, no matter what you try to mess it up, it will always be able to find its way back to an equilibrium position. And what does equilibrium mean? As I mentioned before, many people have a wrong idea of what we mean when it reaches chemical equilibrium. Many people hear the word equal in equilibrium and they think you have equal amounts of everybody on both sides of the arrow at that point. And that is absolutely not what equilibrium means. Equilibrium actually means what we were just talking about in the last chapter. It means that the rate of that forward direction will eventually equal the rate of the reverse direction. So that is what is meant when we talk about a reaction that reaches equilibrium is really the rates of the reactants going to products will then equal the products heading back the other way. What does that mean in terms of reality of what's happening in the equation at that point? What it means is if something is going to the right just as fast as it's coming back to the left, what that means is you're ultimately going to get no change that's going to occur. Everybody's going to get locked into place. So whatever their concentrations are when it reaches equilibrium, they will be able to maintain those concentrations indefinitely. They'll just keep going back and forth. And just as soon as the load gets lost, it'll come back the other way and it'll just kind of go back and forth. And everybody gets locked into place in terms of their concentrations. They get locked into place in terms of their pressures, if you're looking at pressures, which we do as well. And they say there, so if we have this reaction, and let's just say that we started with like initially 5 moles of A, 5 molar of A, 2 molar of B, and nothing of the products. And when it reaches equilibrium, maybe we got like 3 molar of A, maybe 1 molar of B, maybe 2 molar of C, maybe 3 molar of D, right? And what this means is each of these concentrations at equilibrium, like I said, they're just now locked into place. There's nothing that's going to really change. They're going to be able to maintain those things along the way. Now, you can do something to screw up the equilibrium, but like I mentioned before, these reactions are pretty resilient in the fact that even if you screw up the equilibrium, it's going to find its way back to equilibrium, and the rate of the forward direction will equal the rate of the reverse direction. Now, to do that, it may at some point along the way need to start making more products to get back to that, or it may need to make some more reactants to get back to that. But eventually, it will self-correct itself, and it will get back to the rate of the forward direction will equal the rate of the reverse direction, and it will reach equilibrium again. In fact, you could screw with the equilibrium as many times as you want. It will just bounce back and forth, and it will continue to get back to that equilibrium. Yeah. It will not. So what we'll see is there is a relationship, and we kind of talked about it a second ago. There's a relation known as the equilibrium constant, and it's basically the proportion of products to the proportion of reactants. And what will happen when we talk about it coming back to equilibrium is that proportion of products will be to reactants will be the same, no matter if you screwed it up one way or the other, and it gets itself back there. And it will always equal really the same number. The only thing that can affect the value of the actual equilibrium constant, as we'll talk about, is temperature. So as long as you keep the temperature the same, it will bounce back and forth. So for example, if we had this reaction, let's just say like, hey, this is red, like if you had just reactants, everybody would be red in your test tube. And if you had products, let's just say, hey, maybe it'll be green. I don't know how you get that, but hey, St. Patrick's Day is coming up. So you'll get green over there. So, for example, we could reach equilibrium, right? And you could get this guy and just kind of put everybody in there and it will get to equilibrium. Maybe you got a color somewhere between red and green, you got kind of that middle color if you mix those together. And then maybe you did something to it, right? And you could force this equilibrium, for example, to the right by doing something to it. And if you did something to it, it will mess up the equilibrium. It'll no longer be that middle color. And in order to fix it, it may have to make more products. So what you might see in like your beaker is It went from like that middle color between red and green, but now it's moved a lot more closer to green. And what that would indicate, for example, is we had to make some more products in that case. And now we have some more products than we did originally. But if you still take the ratio of the products you have at the end when it turned green to and the reactants, that ratio would be the same as the ratio of products you had and reactants you had when it was like that middle color. And then if you're at green, you're like, hey, I don't want green. St. Patrick's Day is over. You could do something to it and send it back the other way. And you could then make that whole beaker now turn red. And then if you change your mind again, you can send it back and make it red, a green, and you can kind of go in the middle and stuff like that. But the end result is, as we'll talk about, is that equilibrium constant, which, as I mentioned before, is really just a ratio of how much products you have to reactants, will always end up being the same number. And that's really what happens when it reaches equilibrium. And the reason, it's the same is you may have different numbers, but the ratio of products to reactants will always be the same. So for example, and I'll do this example probably a little later on as well. Let's just say we want an equilibrium constant that was like 2, for example. And 2 represents, it's at equilibrium at this temperature, right? Now there's many different ways you could get to 2 by dividing like a fraction, right? You could get 2 by taking 4 divided by 2, right? That equals 2. You could get 8 divided by 4, that equals 2. You could get 2 divided by 1, that equals 2. So although we do have different numbers for everybody, right? The ratio that ends up being the same. And that's basically what happens when it reaches equilibrium. So to answer your question, it may go back closer to that 5 or whatever it may be, but it may be, but everybody else will kind of adjust accordingly, and it'll always end up kind of the same ratio, and that's what happens when it reaches equilibrium. Yeah. Yeah, it's not really the reaction quotient, but it's similar. It's what's known as the equilibrium constant, and it is basically what capital K is. It's what we were just talking about when we are talking about the rate of the forward direction divided by the rate constant of the forward, and the reverse direction is what the equilibrium constant equals. And it's a constant value for a reaction at a specific temperature. And some of the things that we'll talk about is you could do all kinds of things. And one of the concepts that is very hard for people is they think, for example, and we'll talk more about when we get there, obviously, but they think, for example, if they did multiple experiments, and let's say in the first experiment you did all reactants, and the second experiment you did all products, or in the third experiment you did a little bit, I'm starting with some reactants and some products all in the beaker together. All of those situations, as long as the temperature stays the same, they will all come to the same ratio of products to reactants when they reach equilibrium. And you'll end up with an equilibrium constant value, which is why it's called a constant value, because it will stay constant as long as you don't change the temperature. Yeah. Well, it wouldn't mess up your lab, and we'll talk more about it. And when I say the only thing that could affect the equilibrium constant, we're definitely for sure talk a lot more about it. But when I talk about that, what I'm talking about is in comparison of, say, the equilibrium constant at, say, 25 degrees to the equilibrium constant at 45 degrees, those numbers will be different for the same reaction. But if the air conditioning broke and the room settled at 95 degrees, why you got your lab coat on and goggles, sweating up a storm, it would maybe have an effect on it. Obviously, if there was a dramatic effect on the temperature, you may see a slightly different one that you might have saw if you did it all at one temperature versus the other. But it would probably level out at the end if you're doing your experiment to a specific value. Do you have a question? The equilibrium condition is basically when a reaction reaches equilibrium, and basically what that means is this right here, is the rate of the forward direction equals the rate of the reverse direction. And when that occurs for a reversible reaction, you've hit equilibrium. And basically what that means, as I mentioned earlier, is at that point, everybody just gets locked into place in terms of their concentrations, their pressures, they won't change. The other kind of interesting thing about sort of this type of reaction is you could do an equilibrium reaction, speaking of colors, and maybe you did an equilibrium reaction and it turns red. So here you did it, you mix it together, and you're like, cool, turn red, the reaction's over. And it may appear that nothing's happening on sort of the big scale there, right? The macroscopic scale. But if you are getting to the microscopic cell and really zoom down in, there is a lot of activity happening to keep that beaker at red. So there's a lot of A plus B going to C plus D. There's a lot of C plus D going backwards. There's a lot of activity. But to you, when you look at it in the beaker, it just looks like we're done, right? There's nothing that's over. There's nothing happening. So in an equilibrium sort of reaction, there's constant activity happening to maintain that. Just like if you did something to that red beaker and it turned to green, there's a lot of activity still happening to keep it at green and not allow it to go any other way. So sometimes people think when they look at equilibrium, it's just like it's over. There's not much changing, but there is still a lot of activity that's constantly happening to maintain that equilibrium at that point. Any questions?